Hello everyone. In this lecture, we want to discuss the number e as a limit. And you know what e is most likely. E is actually the base of the natural logarithm. It's an irrational number. It's roughly 2.718281, just like pi, which is 3.1415926. So this number e is also an irrational number. And it's a non-terminating, non-repeating decimal number. And we want to talk about that as a limit. So for this purpose, we have three columns here. One column is the variable n, which we will select different values for that. And then 1 plus n, clear, 1 over n is clear. And we're going to investigate numerically to see what will be the value of 1 plus n raised to the exponent of 1 over n. So if I add 1 to n, I have selected some values for n already. If I add 1, so 1 plus 1 would be 2, obviously. And if I add 1 to 0.1, it's going to be 1.1. If I add 1 with 0.01, which is the selected value for n, it's going to be 1.01. And then 1.001 would be the outcome if I add 1 with 0.001. And similarly, 1.00004 zeros and 1. And if I select negative 1, if I choose n to be negative 1, then 1 plus n will be 1 plus negative 1, which is 0, if you think about it. And then if I select n to be negative 0.1, then 1 plus negative 0.1 would be positive 0.9 actually. And then we have 0.99, 0.999, and then we're going to have 5 nines here, 0.999. And that's because 1 plus negative 0.00001 would be 0.99999, obviously. And then in the next column, we have 1 over n. So obviously 1 over 1 is 1. 1 over 0.1 is going to be 10, because 1 divided by 1/10 is 10. 1 divided by 0.01 would be 100. Then we're going to have 1,000. Then we're going to have 100,000, because 1 divided by 0.00001 would be 100,000. And similarly, if we do the same thing and calculate 1 over n, we will end up with negative 100,000 here, and negative 1,000, and negative 100, negative 10. And this last one, if you divide 1 by negative 1, you will end up with negative 1, obviously. Okay, so now we have these numbers in the second column and the numbers in the third column. What we have to do, we have to do a numerical investigation. We grab the calculator and we're going to grab the numbers in the second column and we're going to raise them to the exponent of the numbers in the third column. So for example, 1.009 raised to the exponent of 1,000, or 1.01 raised to the exponent of 100, or like 0.99 raised to the exponent of negative 100. And we're going to investigate with the calculator to see what values we end up with. So that is what we want to do. So 2 to the exponent of 1 is going to be 2. 1.1, I use my calculator, 1.1 raised to the exponent of 10. I get 2.5937426. 1.01 raised to the exponent of 100. It gives me 2.7048133829. Then 1.001 raised to the exponent of 1,000 this time. I get 2.7169233932. 1.12340 raised to the exponent of 100,000. So that gives me 2.7182682237. And I go down, we have 0 to the exponent of negative 1. 0 to the exponent of negative 1 is clearly undefined, so we can't find a value for that. But the next one is 0.9 raised to the exponent of negative 10. So I get 2.8 this time, 6797191. The next one would be 0.99 raised to the exponent of negative 100, which is 2.731999026. Then we have 0.99 raised to the exponent of negative 1,000. All right, so that is 2.7196 I bet you get the same answer on your calculator. So 5 nines I put there, raised to the exponent of negative 100,000. 100,000 has 5 zeros. So I get 2.71829542. Okay, so when you look at all these numbers, you notice something, that 2 is always there. So we see that 2 is always there. And even here we have 2. And then we have 0.7, which is repeated. And then 1 is repeated, and then 8 is repeated. Same thing happens here. 7 keeps repeating, and then 1 keeps repeating, and then 8 and 2 keeps repeating. So you see that there is a sort of pattern here that is revealing itself. So 2 keeps repeating, 7 keeps repeating, 1, 8, 2. These digits keep repeating over and over again. As n approaches 0, as n becomes smaller and smaller, now from the right side or from the left side, it doesn't matter. As n approaches 0, we see that this limit of this power approaches some sort of weird number, and this number, sure enough, is the number e. And the answer, if you keep selecting values for n that are even closer to 0, you will end up with 2.718281, 8284, and then 59045. So it doesn't even stop here. It's going to continue. So dot, 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 I put it there. So this is going to be that number, which we call it the number e. We show the number e, and it appears that this limit of 1 plus n to the exponent of 1 over n actually does exist, and it has a value very close to this non-terminating, non-repeating decimal number, which is 2.7, as I said before, accurate to 15 decimal places. This irrational number is called, of course, e, as I said, and why letter e? It's in the honor of the 18th century Swiss mathematician, Leonhard Euler, from 1707 to 1783. You know the history of mathematics. You better go and do a little bit of research. He became blind later on in his life. He was one of the genius mathematicians out there in the 18th century, and he lived all through the 18th century. The definition of this irrational number e in calculus is given by this limit formula. So if somebody asks you, what is the limit of 1 plus n raised to the exponent of 1 over n, when n approaches 0, the answer is, of course, e. And e is, of course, this number. Now, there's a second version of this formula, and that is when n approaches infinity instead of approaching 0, but then inside the brackets, instead of having 1 plus n, we have 1 plus 1 over n. And then the exponent, instead of being 1 over n, it is actually n. Because think about it, when n approaches 0, 1 over n, the exponent approaches infinity. And here, we're saying that n directly approaches positive infinity. So it's the same thing. Inside the brackets, n approaches 0. But here, inside the brackets, 1 over n approaches 0 again if n approaches positive infinity. So it's just another version of that formula, and obviously the answer is going to be the same. So it was an interesting numerical investigation, and we discovered this number e. Actually, if you keep doing that, correct the 15 digits after decimal point, this is going to be the answer. Roughly, it's 2.7. okay? Pi is 3.14, roughly, okay? All right, now there's an exercise here. It says, what is the limit of 1 plus 6x raised to the exponent of 2 over x when x approaches 0? Now, the thing is that if x approaches 0 inside the bracket approaches 1, and then the exponent approaches infinity, and now you're scratching your head and you're saying, okay, what is this 1 to the exponent of infinity? We have never seen that before, and you are right, actually. If you recall in one of the lectures in the past, I mentioned that there are 7 indeterminate forms in the world of calculus, 2 of which we have already learned, 0 over 0 and infinity over infinity. And this is the third indeterminate form. 1 raised to the exponent of infinity is another indeterminate form in the world of calculus. Unlike what some people might believe, they say, oh, any number, like 1 raised to the exponent of any number is going to be 1. Well, you are right. You are right about that. But infinity is not that any number you are talking about. So 1 to the exponent of infinity, the third indeterminate form that we have learned so far. Okay, how do we deal with this question? We are going to let 6x equal to n, and then from there, x would be n over 6, right? And we're going to say if x approaches 0, then 6 times x, which is n, will also approach 0, logically speaking. So we can say that this limit can be rewritten as limit of 1 plus n instead of 6x, and we can say n approaches 0. But about the exponent, which is 2 over x, I can say 2 over x is actually 2 over n over 6, which is 12 over n if you simplify it. So that's going to be 12 over n. So instead of finding the limit of 1 plus 6x to the exponent of 2 over x, we find the limit of 1 plus n to the exponent of 12 over n. Equivalently, the original variable, the main variable is x. X is approaching 0. Here, the original variable is n. So what we did here was a change of variable. By this substitution of n equals 6x, we changed the variable, but we didn't change the question. So if you find this limit, it's just like you have found that limit. They're equivalent. Now, to continue with this, I'm going to say this is limit of 1 plus n to the exponent of 1 over n, and then the whole thing raised to the exponent of 12 according to the exponent laws, because you know that according to the power of power exponent law, you have to multiply the exponents. 12 times 1 over n would be 12 over n. So instead of saying 1 plus n to the exponent of 12 over n, I can say we have 1 plus n to the exponent of 1 over n, and then the whole power raised to the exponent of 12 back again. Now, this is limit of a power. And I remember when we were discussing the properties of limits, I said that limit of a power is equal to the power of the limit. It was one of the properties of the limit. So I can say this is actually a limit of 1 plus n to the exponent of 1 over n, okay, when n approaches 0. And then this whole thing is raised to the exponent of 12, okay? So I'm finding the limit of the inside, and then whatever that is, raised to the exponent of 12 will be the answer. But what the limit of the inside is what we just discovered earlier. That's e, isn't it? So the answer is going to be e, but then raised to the exponent of 12. Therefore, this limit of 1 plus 6x to the exponent of 2 over x when x approaches 0, which used to be indeterminate form before, now we know that the answer is e to the exponent of 12. By investigation method, by this numerical investigation method, you can also find these 2 other limits, which are famous, and you can construct columns, by yourselves if you want, and you can find out that the answer to this limit of e to the x minus 1 over x is 1, and the other one is going to be ln of 2. Limit of 2 to the x minus 1 over x when x approaches 0, you will figure out that it's going to be equal to ln of 2, and this other limit of e to the x minus 1 over x when x approaches 0, will equal to 1 if you do that investigative approach. Okay, so we discussed the number e, irrational number e, as a limit, and we learned about the formula and the second version of that, and we did one example, and I hope you understood how to deal with these kind of limit questions. Thank you for your attention.